We'll understand flux of gravitational intensity. And first of all, what is flux of gravitational intensity? Let's say this is a surface. We have a mass m here, and from here we have a point which is this, and normal to this area is this area. Let's say this area normal to this is ds. So this, if this is alpha, this will be cos alpha, ds cos alpha. So E into ds cos alpha, that is the flux emanating out of this. Consider this a closed surface. So this is the flux emanating out of this closed surface. You have seen this concept in electricity also. Again, let's say this is at an angle of alpha to the normal. So what will it be? It will be ds cos alpha to this side, and E is the gravitational intensity. So E into ds cos alpha is flux of gravitational intensity. Clear? Now we have Gauss's theorem on this. Gauss's theorem on gravitational flux. It says that En into ds, that is the intensity into ds, surface integral, is equal to minus 4 pi g into the total mass enclosed within the surface. The total flux of gravitational intensity coming out of an enclosed surface is this En ds 4 pi g sigma m. This is called this is Gauss's theorem. And by using this theorem, we can find the gravitational intensity due to a body of mass m. See how much it is easier to find if we have a sphere, let's say of radius r, and we want to know what is the gravitational intensity at a distance r. Either we can use calculus. For example, we'll take one dx this size and then integrate it from 0 to r and all. This is the first way in which we find. But here what we'll do, we'll use Gauss's theorem. It will be very easy. See, first case is at any point outside the sphere. What we are seeing? Gravitational intensity due to a sphere. First case, at any point outside the sphere. That is, if this is a sphere of radius r, and we want to see what is the gravitational intensity E at a distance r from this. Let the mass of this sphere be m. So what we do? It is E surface integral En into ds minus 4 pi g into total mass enclosed. Total mass is 4 pi gm, that we know. What is this? This will be E into the surface area. What is the surface area of the sphere? It is 4 pi r square. This is the surface area of sphere. So this is equal to minus 4 pi gm. Now 4 pi cancels. So E is equal to, what you have? Minus gm by r square. This expression, this deduction we have seen earlier also. So this E is minus gm by r square. Okay, clear? Now second case, at any point on the surface, that is, let's say at this point. Again, E into, this is 4 pi r square, this is r square. There was this, the surface area was this due to r, small r, and here this is this r only, the radius of the sphere. So this is 4 pi g into mass is m. So what you get is E is minus gm by r square. Okay, again we have seen this result. What will be the gravitational field intensity at a point inside the sphere? At a point inside. Let's say now r is at this point. This is small r. Let the density, volume density be this. This is the volume density of the sphere. Okay. So what is the mass? Mass will be 4 by 3 pi r cube. This will be the volume into rho. This is mass. So sigma m will be this, and area will be, this is, if the intensity is E, this will be E into 4 pi small r square. This will be equal to minus 4 pi g into Mass is this, that is 4 by 3 pi r cube into rho. So 4 pi cancel, r square cancels this, only this one. So E will be equal to minus, what we get? We get 4 by 3 pi g r rho. So this is the gravitational field intensity inside the sphere, where the radius be smaller. Clear? And if you want to see this expression in terms of m, what will be m, mass of the sphere? This will be 4 by 3 pi capital R cube into rho. Okay, so you can express this small mass m was 4 by 3 pi R cube rho. You can have this. So from here you can take the value of R rho, that is this ratio you can take out and then you can put it here. Okay, now let's see, this was our sphere. Now let's see the same values for a spherical shell, that is not a solid sphere. So for a E for spherical shell, first at some point r that is greater than r, we know it will be E, this surface integral E ds will be E into 4 pi r square, small r square, and the total, this will be minus 4 pi g into, if the mass is m, let's say the mass is m, so this only. So from here what you get, it will be same, that is minus g m by r square. Similarly, when r is equal to r, this will be r square, and so what you will get is E minus g m by r square. No issue. Third one, when this small r is less than r, that is less than radius. Here this sigma m will be 0 because the spherical shell is empty inside. So what you will have, E will be 0. Okay. Let's discuss Kepler's law of gravitation. There are 3 laws. First law which is called law of elliptical orbits. First law says that it is related to our solar system. So it says that the planets revolve around the sun in elliptical orbits. Any planet, if we are talking of Earth, let's say this is sun, then Earth rotates in an elliptical orbit around the sun, if this is Earth. Okay, and sun actually, it is at one of the foci that we call. So it won't be here, it will be somewhere around this. You know about ellipse, you have two focus here, one focus here, one focus here. So sun is at one of the foci and the planets revolve around it in elliptical orbits. This is law of elliptical orbits. First law given by Kepler. Second law is called law of equal areas. Not equal area, law of areas. The law is called law of areas. Okay, let me explain it. What is law of area? It says, if this is an ellipse, let this be the focus at which sun is residing. So you know what is major axis and minor axis? It says when it is this, and let's say this in dt time, the planet is at this position and then it goes to this position. So you'll have, let's say this area is del A, and when it is here, if it is at this position is traveled by the planet. If this area is del A, then the time will be dt only. That is the aerial velocity dA by dt, aerial velocity, aerial, that is area, related to area. So area velocity is a constant. This is Kepler's second law. Okay, we are not going into proofs. It is a very lengthy mathematical proof that is not required in engineering. You have to understand the laws only, the concept only. Third law is called harmonic law. What is this? It says that square of the time period. Time period, what is time period? Earth revolves around the sun in 365.3 days. That is the time period. So square of this is proportional to the cube of the semi-major axis. You have semi-major axis, so square of this is proportional to cube of this. So if let's say this is Earth and this is Jupiter, if this ratio is let's say 1 by 30, okay, that is semi-major axis of Earth, semi-major axis of Jupiter is 1 by 30, let's say, and we know what is time period for Earth. So TE square by TJ, where TJ is time period for Jupiter, will be equal to, this is TE by TJ, so this will be AE by AJ, that is 1 by 30 cube. That is, you can say TJ will be equal to TE, this side cube, so 33 by 2 into this. So you'll have figures given and you can find the answer, 365.3 days, and then you can put the value and you can see what is the value for Jupiter. So these are the three laws given by Kepler. These laws should be understood. They should be kept in mind.